Last class we were talking about the three-phase, how to generate three-phase waveform based on individual pole voltages with a 120 degree phase shifted, and for three-phase how to connect suppress the triplet order by removing the neutral. Okay. So, we will again start from there. So, that let us draw the waveforms once again. Okay. This the, let us say for the A phase, the pole voltage waveform will be like this. Okay. This is the A phase waveform, square waveform. Okay. A phase waveform, again we will draw it for continuity here. This is our Vs0 pole voltage. Okay. Let us say our omega t starts from here. This is Va0 Vdc by 2 and minus Vdc by 2, and Vb0 pole voltage will be 120 degree phase shifted. So, Vb0 will be 120 degree phase shifted. This will be so with respect to 120 degree means it will happen here. Okay. So, this is our Vb0, 120 degree phase shifted, Vb0. Now, Vc0 pole voltage again 120 degree phase shifted with respect to B phase. So, it will be from here 120 degree phase shifted means, let us draw the axis first. So, 120 degree means it will be starting from here. Okay. This is our Vc0. Now, for the inverter, we said, let us draw the inverter here. You are assuming bidirectional switches. Okay, A, B, C, A, B, C. So, our load is like this. Okay, it comes here, it comes here, C means it comes here. This is our neutral N. So, and this is our fictitious O, VDC by 2 and VDC by 2. See, this O, this is not, we are not using two DC link VDC by 2, VDC by 2. For analysis, we are trying to measure the various pole voltages with respect to the fictitious center tap. Okay. Now, we told before, this is derived from our basic configuration, our single phase half bridge converter. So, this connection, neutral connection we have removed and all the triplen will be removed. Okay. Now, we know that we have also derived our VAN, VBN, VCN equations. Okay. VA0, so VA0 is equal to VAN plus VNO and VB0 is equal to VBN plus VNO. NO is the voltage from here to here. So, VA0, if you measure this voltage is equal to VAN plus VNO. Okay. Similarly, VC0 is equal to VCN plus VNO. And by summing, we found that VA0 plus VB0 plus VC0 by 3 or by 3 is equal to VNO. Okay. So, VA0, VB0, VC0 divided by 3 is equal to VNO. Substituting this one, we know VAN is equal to, we have derived VAN is equal to, I can write it here, VAN is equal to, we have derived VAN is equal to 2 by 3 VA0 minus 1 by 3 VB0 plus VC0. Okay. So, if I remove this one, we can write it neatly once again. I can write here VAN is equal, substituting this value VN0 in our VA0 equation, we can find out VAN is equal to 2 by 3 VA0 minus 1 by 3 VB0 plus VC0. Okay. Now, using this equation, let us find out our VAN here. Okay. We will try to find out the VAN here. So, let us draw the line here for x axis. Our omega t starts from here, that is what we said here, from here. So, if you see the 60-degree interval period, that is this one, there is a change in pole voltage every 60-degree interval period. So, the VAN, that shows VAN will be stable for 60-degree interval period, and every 60-degree interval it will be changing. Let us say first 60-degree interval, VAN is equal to 2 by 3, that is this one, 2 by 3 VA0 minus 1 by 3 VB0 plus VC0. So, 2 by 3 VA0, 2 by 3, so here VAN. See, VB0, VC0 are opposite, that means it will cancel. Now, this is VDC by 2. This is VDC by 2. So, VDC by 2. So, VDC by 2 into 2 by 3. 2 by 3 is equal to VDC by 3. So, here it will be VDC by 3. Let us draw the waveform here. This is VDC by 3. Let us see, this is VDC by 3. This amplitude, I would say this is VDC by 3 from here to here. Now, next 60 degree interval, VA0 and VB0 are negative. So, minus VB0 plus VC0, they are negative. That is equal to minus VDC by 2 minus VDC by 2, that is equal to VDC by 2. VDC by VDC minus VDC, and minus 1 by 3 it will come plus, it will come to plus VDC by 3, sorry, plus VDC by 3. Okay. This is the effect of these two portions, VB0 minus VDC by 3. Then our 2 by 3 VA0, 2 by 3 VA0 is again VDC by 3, like here. So, VDC by 3 plus VDC by 3, it will equal 2 VDC by 3. So, it will go 2 times from here. Okay. Now, if you see, it repeats, it repeats like this. This is the positive half cycle, then this is the negative half cycle. If you do the Fourier series of this one, this will not contain triplen order. That means this will contain fundamental, 5th, 11th, 13th, all harmonics only. 3rd, 9th, all these harmonics will be absent. All this triplen order will be across this VNO. Because triplen order, if it is there in the phase voltage, all the triplen order will be in same phase and there is no return path. So, the current, that current will not have a return path. So, current is not there. So, in these voltages, the triplen order won't be there. The triplen order will be dropped across this point, neutral and the O. Okay. This is the A phase waveform. Now, B phase waveform will be 120 degree phase shift. Okay. That we can draw. Once you get the thing, other thing we can easily get. This is 1/3, 1 by 3 VDC. This will be 2 by 3 VDC, this height. Okay. So, if you do the Fourier series of this one, the peak fundamental V1 maximum will be 0.637 VDC. This you can do the Fourier series and you can find out. So, for this waveform, the maximum V1 maximum will be 0.637 VDC. Okay. So, the pole voltages are switched in a rectangular pulse with a 180 degree on and 180 degree off. Okay, with the magnitude is equal to VDC by 2 and minus VDC by 2. If you do it pole voltages, the phase voltage will have a 6-step waveform like this. This is 6-step waveform. So, that means in one cycle, to make a one cycle, it goes to 1 step, 2nd step, 3rd, 4th, 5th and 6th. So, you can say a 6-step waveform. So, this is also called a 6-step waveform. This is the phase voltage waveform, VAN, 6-step, and it will have a maximum fundamental of 0.637 VDC. This you can 0.637 VDC. This you can do the Fourier series and you can find out. Okay. Now, with the 3 phase also like our single phase, Frequency we can control by controlling the on duration, off duration of our pole voltages. Only thing, the ABC has to be 120 degree phase shifted with, B has to be 120 degree phase shifted with respect to A, C has to be 120 degree phase shifted with B. Okay. So frequency can be controlled, but here also the problem is the voltage cannot be controlled. Now, for 3 phase, so let us say if it is a motor drive applications or UPS applications, 3 phase, this voltage control we can use our sine triangle PWM. Okay. So we have studied about the sine triangle PWM. Let us revise once again that one. Again let us draw our single phase half bridge basic converter. Okay. This is VDC. Okay. S1, S2. This is our load A, this is 0, this is VDC by 2, this is VDC by 2. Okay. We are using sine triangle PWM, and so we will have a triangle waveform of fixed amplitude. Let us draw it. This is our triangle waveform. And we use a triangle waveform, the frequency of triangle waveform is much higher than the triangle waveform. Okay. Also, we will use the triangle frequency is an odd multiple of sine frequency. So the PWM, the positive, will have also an odd symmetry. So we will come to that one now. Okay. Now let us draw our triangle waveform, a sine waveform. So that is called the modulating waveform. So triangle waveform is called the carrier waveform. So let our modulating waveform will be like this. Okay. Now, as I told before, the switch sequence, sine greater than the triangle, top switch is on. Top switch is S1 on. And that time when S1 is on, S2 is off. Okay. Next, when sine less than triangle, that is our carrier wave, S1 off and S2 on. This is the switching sequence. So when S1 is on, we know it is pole voltage is VDC by 2, this is minus VDC by 2. So if you see, you will have VDC here, if you see, sine is greater than the triangle, so it is this point, so VDC by 2. Then during this portion here, sine is less than the triangle, so you will get minus VDC by. So if you see here, our pattern will be like this, and the width of the pattern in a triangle period varies proportional to the amplitude of the sine wave. That means the area of the portion increases sinusoidally. This we have, and we have also analyzed in the context of front end AC to DC converter that the output fundamental will be proportional to the sine wave. Okay. And using the odd symmetry here and with the large carrier frequency, this also not only proportional in amplitude, the phase also. In all respect, it will be exactly proportional to the sine wave fundamental. Okay. So now this is the negative portion. Negative portion, negative side, after that is the portion, the pulse width waveform pattern after 180 degree exactly opposite to that of the pattern before 180 degree. Okay. So, the fundamental, if you see here, fundamental we can use a different color for clarity. That fundamental will be like this. So, fundamental amplitude will be proportional, or the fundamental will be proportional to the our VMT waveform, that is VMT, modulating waveform. Okay. So, by varying the amplitude, this fundamental can be controlled, and also here for 3-phase operation, what we do, we will add 3 more lugs. Same triangle we can use, but the sine will be, because we want the fundamental. So, sine will be 120 degree phase shifted. Okay. And exactly for 3-phase waveform. So, before coming to 3-phase waveform, let us see these harmonics of these waveforms. Harmonics we have studied, correct? We also talked about the harmonics in the last in the context of front end AC to DC converter. Harmonics will have, you have the fundamental, that is fundamental frequency, this is F, that is at FM, then you have at FC, then side bands, FC plus 2 and FC minus 2. Okay. Then you have at the 2FC side bands, that is 2FC plus 1 and 2FC minus 1. Okay. This way harmonics goes. Again it will have the same repeat at 3FC and 4FC you will have the side bands, it will go. So, the harmonics amplitudes, if you see here, it will decrease like this. Okay. This way it goes, harmonic. So, the purpose of doing the PWM was to, or is to control the output in proportion to our control voltage the VMT, and also we want to shift the high order, high amplitude harmonics to the high frequency side. So, here if the FC is take it 11 times, so the high amplitude and FM is 50 hertz, the FC will come, the FC will be at 550 hertz, 11 into 50, so far away. So, if you see here, all the 3rd, 5th, 7th, all the harmonics will be highly suppressed. So, what is the advantage? So, in the load voltage, even though it is present in the load voltage here across AF0, the current drawn by these harmonics amplitude is much less and current will be nearly sinusoidal with a small ripple. Okay. Now, suppose if I am using for UPS application this one. So, UPS we want a pure sine wave. So, the purpose is to suppress the harmonics. Now, for UPS applications, suppose if you want some UPS application, we want a pure sine wave outside output, and in some cases we do not want to have high switching frequencies. So, harmonics has to be suppressed. So, sometimes we need to have some filter. So, filter size, if the high amplitude harmonics we can shift it to the high frequency side as much as possible, the filter size, especially the inductance part, a filter will be a LC part, inductance size and the size can be, inductance value can be reduced and the copper size can be reduced, there will be a saving. So, how to suppress this harmonic without resorting to high frequency switching? Okay. So, like our front end AC to DC converter, to remove this one, so with our sine triangle comparison with this one, we have got the fundamental amplitude variation control. Now, to limit this one, we require one more degree of freedom. So, let us see. In this case, if you see the output is going +1 and -1. Okay. Now, let us go to the next page. Our converter is like this. You have for UPS, let us say this is the battery. Okay. So, this is A, this is B. Our load is connected here. Okay. Now, we know that this is 1, 2, 3, 4. These two legs can be independently switched, and we want independently switched so that the fundamental VA0, 0 means the fictitious center tap here, VA0 and VB0, fundamental should add, and the harmonics at the harmonics at this should cancel. That means the fundamental should add and the harmonics, this harmonics should get suppressed, and we are using the same PWM technique, sine triangle PWM, such that we have to use it such that the VAB is equal to VA0 minus VC0. VA0 is equal to VAB is equal to VA0 minus VB0. If we have the one more limb here. Okay. Now, the load is here. This is our B. This is this is not the way to connect when you have two limbs here. Okay. Now, if you see here, the fundamental of VA0 and fundamental of B0 should be, it should be in same phase. No, sorry, it should be in opposite phase, because we are using VA0 minus VB0. And this one to cancel, FC to cancel, all these harmonics due to VA0 and VB0 should be in the same phase. So, when you subtract same phase, it will get cancelled, because AC waveform same phase means is exactly they will cancel each other. So, how to do it? So, let us go to our figure here. Again, let us draw our sine triangle. We will go to a different color. This is our x axis. Okay. Again, this is our triangle waveform. So, here also we will use a triangle waveform, which is the frequency of this carrier waveform is much higher than the sine wave. Okay. Okay. Now, here we do one thing. The triangle frequency, the frequency of the triangle waveform, that is FC is an even multiple of our FM. FC is equal to, FC is an even multiple of the FM, that is sine wave. Previously, we are using 11 times. Here we will use 12 times. Let us take, that is equal to even multiple of, no, not FC, FM. That is equal to, that is, we can write here that we can write FC is equal to, let us say 12 FM. This is an even multiple. Okay. Now, let us draw our also for the A phase and B phase, the fundamental should be in opposite phase. So, we will use 180 degree opposite sine waves or modulating for the two legs. So, that we can draw it like this. Let us take a different color. Okay. So, we will use the sine wave like this. This is our modulating wave. Okay. For let us, this is for the modulating wave for pole A. Then pole B we will exactly 180 degree phase shifted. We will use it. Only thing, this is odd multiple. So, that can zero crossing, you know that it is happening somewhere here. Somewhere here it is happening. Okay. So, this is the zero crossing happening here. Okay. Now, if you draw the PWM, that means FC is 12 FM. So, for the VA0, the pole voltage waveform will be like this. We can draw this way. This will be sine is greater than the triangle, top switch is on. So, it will go like this. So, the area or the width of the pulse increase in a sinusoidal way. Okay. Here it will reverse. So, whenever sine is greater than the triangle, we are turning on the top switch. When the sine is less than the triangle, we are turning on the bottom switch. That is for the leg A. Okay. So, the PWM pattern, if you see here, these are the portions during which top switch is on, bottom switch is on. Here the top switch is on. So, you can see the width slowly increases in a sinusoidal way. Okay. Here it is like this. Okay. So, if you see here, it slowly comes here, equal durations at the cross or equal duration positive negative, then here the negative side it slowly increases. So, if you say the fundamental of this one will be proportional to the our VM, that is VM for, that is this is the one, VM for A phase, okay, and this one is VM for B phase. Okay. So, this is the way it changes. So, VA0 will be like this. Same way we can write the VB0 also. VB0, so this is VDC by 2, this is minus VDC by 2. Okay. Now, for the other phase, we will draw it like this. Maybe we can use a different color. Okay. So, now with respect to this sine wave, sine is greater than the triangle, top switch is on. Okay. So, here see this triangle is this way. So, sine is, so sine amplitude is greater than the, so if you see here during this portion, sine is greater than the triangle. So, which switch will be open? We will be turning on the top switch. So, the pattern will be like this. here also the area during a triangle period, it varies proportional to our sine wave. Now the sine is, so this is the way. Okay. Now the area started increasing at the positive direction. Okay. So if you see these two patterns, the patterns are exactly the same with a 180-degree phase shift. So this pattern and these patterns are exactly same with a 180-degree phase shift. So this 180-degree phase shift happened because of the fundamental. Okay. So fundamentally is 180-degree phase shifted. So the harmonics which is 12 times, that's even multiple. What will happen to that one? 180 into 12, it will be 360-degree. That will be in the same phase. So all the harmonics at FC and its side bands will be in phase, but the fundamental is opposite phase. So if you subtract, if you see the subtraction, the final will be a pulse amplitude of VDC, positive direction. So you will get something like this. I am subtracting VA0, this is VA0, this is VB0. Now let us draw the pattern. VA0 minus V0, this height will be VDC. So let us draw the x axis. So we are subtracting the instantaneous VA0 and VB0 waveforms. Okay. See, here during the positive cycle, if you observe, the waveform is going from 0 to VDC, and the negative cycle, it will be going like this. So this variation also in a sinusoidal way, and this fundamental of this one will be 2 times VA, V 2 times the modulating wave for A. So because we are fundamental of VA0, VB0 are 180-degree phase shifted, when you subtract, both will get added. So we will get an increased fundamental here. At the same time, see, we have used 12 times the modulating frequency for the carrier wave. So here the fundamental will be like this. Okay. Now, so fundamental get added, but carrier frequency at FC. Now the FC, if you see here, FC is equal to 12 times FM. 12 times FM, and if you see the pattern here, these two patterns VA0, VBs are exactly same with a 180-degree phase shift. This 180-degree phase shift is with respect to the fundamental. So fundamentally is 180-degree phase shifted. So 12 times fundamental, how much it will be? 12 into 180 will be, this will be in same phase, that is is a multiple of 360. So, this will be a some multiple of 360. So, that means even harmonics, all even harmonics, that is at Fc and its side bands will be in same phase, and when you subtract it will get cancelled. So, if you see the FFT spectrum for this one, we can draw the FFT spectrum for this one. You have the fundamental, then all at Fc will not be there, it will be highly suppressed, Fc will not be there, and you will have the next harmonics that happens at only side bands of 2Fc here. This is Fc plus 2Fc plus 1 and 2Fc minus 1. So, it is shifted. So, the higher amplitude harmonics here, it is shifted to the 2Fc side here. So, these type of waveforms are these are called unipolar waveforms. Okay? Unipolar, that means one side it is going to positive, other side it is negative. So, the shape is because compared to this one the Fc is cancelled. So, what is the advantage? We can use this one for UPS applications. What is the advantage? Then the filter required its cutoff frequency we have to design with the 2Fc. So, filter size requirement can be reduced. And so, this way appropriately phase shifting the sine triangle carriers, the sine triangle waveforms, and appropriately choosing the triangle carrier frequency, many ways we can control the harmonics. So, another way of controlling the harmonics we have studied in the context of front end AC to DC converter. So, the whole purpose here was to control the fundamental and suppress the low frequency harmonics. Okay? Then is there any other way we can do it? Can we do it? And so far PWM technique we have talked about single phase case. For 3 phase case, same triangle, but the modulating wave should be 120 degree phase shifted. Then we can appropriately switch the pole voltage, because for a modulating wave, what we are saying for a leg, when the modulating wave or the sine wave is greater than the triangle wave, we are switching on the top one. When the sine is less than the triangle wave, we are switching on the bottom one. So, the sine wave, if it is 120 degree phase shifted, the same technique can be used for our 3 phase case. That means, for the 3 phase case, we will be adding one more limb here. Okay. Now, our load connection is not like this. So, here this is our B, 3 phase, this is our C. Okay. Now, our load connection is like this. Okay. Yes, schematic representation for the 3 phase, it is like this, B will be like this and C will be like this. Okay. This is our N, will not be connecting here. So, the pole voltage ABC, so all the switching depends on, we are concentrating at the pole voltages. Okay. Harmonics are suppressed, triple N harmonics are suppressed because of the neutral is not there. So, pole voltages will be switched with respect to sine triangle PWM. When the sine is greater than the triangle top, for the A phase, sine is less than the triangle bottom switch. For B phase, same triangle waveform like this, but the sine will be 120 degree phase shifted somewhere here. Okay. That will be using for the B. C phase again, it will be another 120 degree like this, something here. Okay. So, that will be using for the C phase. So, my wave sine waves are not correct, but you can draw it. So, this way we will be controlling the ABC sequence. So, as I told, the whole purpose was to control the harmonics and also to control the low order harmonics and also to control the fundamental. Then what we achieved, we have introduced the notches instead of the rectangular pulse. Okay. Equal on and equal of rectangular pulse, we introduce notches, in between notches. That means positive side part of the time it will go in negative, and the negative side it is part of the time go positive. So, notches are introduced so that the harmonics are suppressed. So, can we introduce notches in such a way somehow the lower harmonics can be suppressed and the fundamental can be controlled? This is called selective harmonic elimination. See, lot of work literature, in literature you can see lot of work on selective harmonic elimination, mainly from academic research institutions, but implementation of this one, especially for variable speed applications, more for a specific application with a fixed fundamental frequencies operation, it may be possible, but for variable frequencies of application, the selective harmonic elimination, that means deliberately introducing notches, requires lots of offline computation, and so it is seldom used in dry environment, but still it is there in literature. We will study about that one. Selective harmonic elimination harmonic elimination. Here we are deliberately introducing the notches in such a way that the waveform, the positive, we are trying to get a fundamental sinusoidal variation. So, the notches are introduced such a way, so the waveform positive half cycle, that is first 180-degree period and the second 180-degree period have correct sines, the symmetry of a sine wave. So, how it is introduced? Let us see some typical pattern for a selective harmonic elimination. Okay. Say we can have, let us take our x axis like, see we introduce notches. So, this is our pi by 2 period, this is our pi. So, let us draw our waveform. You have here notches we will introduce like this, exactly pi by 2, that symmetry, if you fold it, this part exactly come on, that is pi by 2 side, it will go there, this is pi, okay. So, introduce notches like this. So, this is the positive half period, top switch is on, this is bottom switch, is on, here top switch, this is the positive half cycle. This exactly will be exactly represented in the second half cycle in the opposite way. So, in the opposite way it will be like this. Okay. So, we have introduced from at the pi by 2 side notches at alpha 2, alpha 1, and here it will be pi minus alpha 2, and here it will be, that is this this point will be pi minus alpha 1. Okay. This is 1. We have introduced in a half period, that is in a half period 2 notches, 1 notch here negative, 1 notch here, and the negative side also 1 notch here, 2 notches with a notch width that at points at alpha 1 and alpha 2. See, we can introduce more number of notches. So, introduce more number of notches, we can control more number of harmonics. So, let us introduce some more notches and see how the typical pattern looks like. So, we will go here, this is our axis. So, we are talking about with a single pole, okay, based on our basic configuration, single phase half bridge converter. This can be extended to the other legs also. So, the pole voltage A, positive, negative, this way goes, it goes, okay. Then it comes here, So, this is the positive plus VDC by 2, during this period minus VDC by 2. This is the quarter wave. So, symmetry, quarter wave symmetry will see if exactly fold like this, quarter waves will merge, same like our sine wave. And the half wave symmetry existing for the sine wave should be there. That means this positive part should exactly go to the negative side. So, we have introduced how many notches in a quarter? See, previously in a quarter wave 1 notch, here in a quarter period we have introduced 2 notches. 2 notches, this is 0, this is alpha 1, this is alpha 2, this is alpha 3, and rest is symmetry from this axis. So, introducing more notches, we can control more harmonics, and at the same we have to control the fundamental as required by the load. So, we will find out from this one, we will write down the harmonics, Fourier series of this one, we will try to find out what is the fundamental and what are the alpha 1, alpha 2, alpha 3 required for a particular waveform to suppress some of the low order harmonics. So, that means if you want to control a fundamental, you require one equation. If you want to control 5th and 7th, we require 2 more equations. So, require 3 conditions are required to suppress fundamental and 5th and 7th. So, if more harmonics to be controlled, you require more notches, more equations is there. So, this way for more harmonics, more equations need to be solved, and this is only for with respect to one fundamental. So, to variable speed operation with the different fundamentals, we require different condition for the notches. So, it requires a lot of offline computation. So, it is seldom preferred in drives environment. But how to find out the suppress the harmonics and how to control the fundamental for the selective harmonic elimination with the general equation we will study in the next class. Thank you.